All right, good morning, everybody, and thank you for coming to my talk today. I am going to tell you about some results of some modeling work that we're doing at Los Alamos, and I want to remind you that the shapes I'm going to show you are going to look very familiar, but I am not actually showing you models of deflecting or of the DART impact or of an attempt against Comet 67P. We're using their reference models as a departure point for our models. So when you see these results, these are not DART experiment results, they are DART adjacent results. So NASA and the agency that I work for, NNSA, the National Nuclear Security Administration, has an interagency agreement that's been going on for several years now, where we are collaborating on models of mitigation attempts against various asteroids. We started with a code-to-code comparison to make sure that we are comparing apples to apples, not apples to rutabagas, and for the most part, we get there. We then did a case study which was published last year about mitigation attempt against the design reference asteroid, what was known before OREX got to Bennu. We used those assumptions, which have turned out to be subtly different from what they saw when they got there, and so it's going to be really exciting to revisit this eventually. We did that pre-orbit model there. And then we went to Goddard and worked with them at the Mission Design Lab to design a hypothetical spacecraft that could attempt to mitigate such an object. We then did case study 2 on a Didymos B-like object. And again, we borrowed the DART team's design reference asteroid, and we are using it for our own purposes. So this is not the DART impact. We've completed those models, and the report is currently being collected and drafted by Brent Barbie at Goddard, so stay tuned for that. And now we're working on case study 3, which we are using the 67P shaped model, scaling it down and using it to study a very asymmetric contact binary with absolutely no volatiles in it. So you'll see that at the end. There we go. And so what we're doing for this at Los Alamos is we have expertise in hydrocode development, hydrocode modeling, equations of state, strength models, shear strength models, opacity and heat and light transfer through materials. And we are bringing all of those to bear on studying this problem. We have, as you might expect, a lot of experience with nuclear explosives devices and with high strain rate phenomena like impacts. And so we're using those to model this problem using our supercomputers and our hydrocode models. And we're getting a lot of early career training out of it. Several of us on the project started as postdocs, including myself, and have since gone on to be research staff at the lab. And we're finding that this problem is a really great way to train staff. Our first case study, again, was, or our second case study, excuse me, was Didymos B-like threat object. This is their preliminary design reference asteroid. So it's about 100 meters across. It is literally pear-shaped. Has about a 25% porosity. You're going to notice that the density that I'm using is a little bit different than what Megan just showed you because DART updated their DRA. We're using a basalt equation of state with a simple P-alpha ramp model. And we have 2 kinetic impactor scenarios that Brent gave us. One is lower velocity, lower kinetic energy. One is a little higher, depending on your launch window. And we study each of those 2 cases, one on the semi-major axis and one on the semi-minor axis for impacts. And we have some analytic model predictions from Holz-Apfel scaling relations and Q*D just to orient us. So for the 2 scenarios, we're looking at betas that are ballpark 1 out of crater scaling. But when we look at the Q*D estimates of binding energy relative to the kinetic energy of our impacts, that's when I start to get concerned because we're starting to see estimates for Q*D that are an order of magnitude lower than the kinetic energy of our impactors. So that was my first clue that we might be in a little bit of trouble here. So here's our first round of scenario results. This is the higher kinetic energy case. And the results I'm going to show you here are from FLAG, which is the free Lagrangian hydrocode. It's one that I haven't shown to this community before, but we've run it through Betty Perazzo's bake-off tests, and that's been published by my grad student, Wendy Caldwell. And so here for our models, to my surprise, we're seeing betas that are an order of magnitude higher than predicted by the 1D scaling laws and are more consistent with the disruption that we were seeing from the Q star D predictions. We're getting delta V's that are a lot higher than V escape, and speculating about what might dial these numbers back a little bit. If we had self-gravity in here, it would slow things down a little bit, change the force balance. If we had some shear and tensile strength, it would matter a little bit. As you saw in Megan's talk, these might not be terribly strong effects, but they would do a little bit. And to look a little more carefully in the second case, here's what I think is going on. So if you look at the figure there, this is this model was done 2D axisymmetric, swept out. So on one side, you've got pressure. On the other side, you've got velocity in the y direction. And you see everything in red there is above the escape velocity. And this is why I think we're getting answers that are so much different from pi scaling, is because in the scaling law models and in most ways people calculate beta, you threshold to ejecta that has moved above your point of impact. And you take the velocity, the momentum of that, and that's how you pull out beta. I didn't want to wait that long because we've got a very low escape velocity here. And if you look at everything in red there, let's see if I can engage the pointer. There we go. All of this material is traveling above the escape velocity, but the escape velocity is of order centimeters a second, and it's got 100 meters to go. And so that's 25 seconds of simulation time. That's a month of my life that I don't want to wait. So I thresholded by velocity and waited until things stopped ringing around, and this layer of spall here is now on a ballistic trajectory. And then I calculated beta using that. So I'm finding a much higher beta here because I'm counting this spall from outside the crater. And pi scaling doesn't do that, and that's not a flaw in the model. That's an intentional simplification. So when Keith's looking at cratering, he's looking at the ejecta here, not at distal spall coming off the surface. So I think this is what's explaining the discrepancy there, and that makes me think that I want to be very, very careful about shear and tensile strength in these models, because that's going to determine what gets kicked off the surface by this release wave as the shock from the impact hits the surface. We also did some models in RAGE. This is work that was done by my postdoc, Amanda Truitt. And so she was thresholding according to the standard practice of everything that goes above the point of impact. And her models had some simplifications, so they ran a lot faster, but ignored phase changes and stuff like that. And she's still seeing betas that are much higher than we would expect from the scaling laws. So that's, again, to be expected, but is something to be mindful about as we're using pi scaling as a heuristic for calculating beta. So to wrap up, again, we do need to be a little careful about using pi scaling for beta. We have both Eulerian RAGE models and flag Lagrangian models that are showing us betas that are a bit higher for these sorts of deflection attempts. This does make me nervous about the sort of assumptions that we're making for the exercise, where we're assuming betas of 1 or 2 for these higher kinetic energy cases. Comparisons to the sorts of kinetic, or the kinetic energy of your impactor versus the Q star D of the object, I think may be a good thing to do. However, the Q star D papers that are out there, while they're awesome, are very preliminary, and a lot of the assumptions about those binding energies are not at the level that we can start to do mission predictions with them. So I would like to provide this as a corrigendum to those thinking about Q star D to please do a lot more of that. All right. Case study 3. Again, this is not a ducky. This is not Comet 67P, with apologies to Renee Magritte. We have the 67P shape model, which we have scaled down to about 200 meters. The equation of state that I'm using for this one is a prototype aerogel equation of state, which allows us to do porosity, hopefully with a more accurate treatment of thermodynamics. We have densities here of about half the density of water, but we do not have any volatiles. This is not a comet. This is a contact binary that we're trying to model here. and will have an escape velocity to orient you of about 3 centimeters a second. We have, again, 2 kinetic impactor cases that Brent gave us based on an assumed trajectory of this hypothetical object. And we have then 2 sets of models for each. One where we're hitting the broadside, the bottom of the ducky coming in like that, and one where we're hitting the head coming in like that. So they're sort of 90 degrees, but they do get to be a bit grazing, because as hard as it is to aim a spacecraft, it turns out it's also really hard to aim these things in a hydrocode. So that's been an interesting digital world meets reality moment. So for these models, I'm again using the flag Lagrangian models, and we're using a little bit of strength for our impactor, but it does pretty much vaporize when it hits. Going back to Holzapfel and Q star D, we're looking at crush craters with beta much less than 1. We're looking at predictions of some very, very gentle deflections, which is a good idea for a fluff ball like this. The Q star D predictions get to be dicey, not as bad as the last one. We have a very broad range of Q star D because the binding energy factors for these fluff balls are not well constrained. That's, if you're familiar with the Dobrovolskis paper, it's the little q is not very well constrained for a puff ball. So we have kinetic energies of our impactors that fall in the range of the predicted Q star D, but that range is huge. So here's what we're seeing out of flag. This is for our second model. It's the higher kinetic energy case. These models are running as we speak on the supercomputers back at home at Los Alamos. We're not converged in beta yet, which is why I have greater than signs there. But we're still an order of magnitude above what pi scaling would predict, because again, we've got a little bit of SPAL, not nearly as much as last time because we're porous, so a lot of that energy is going into crushing things out. So that's hopeful, but you do see on this model here, anything gray is below the escape velocity, anything in color is above the escape velocity, blue is barely above the escape velocity. And so a lot of that I think will actually settle down, as this is more of a shock velocity than a particle velocity in this case. So to wrap up, we have completed some models of kinetic impactor mitigation attempts against a Didymos B-like solo asteroid. This is not the DART impactor. Please, Angela, don't stress out about my results. This is a totally different situation. We're also calculating kinetic impactor attempts against a bilobate, dry but highly porous hypothetical asteroid. And we're seeing scaling relation predictions that are very different from what we're seeing out of our hydrocodes, but also what we're seeing out of energy of disruption sort of calculations as well. Again, I would really like to encourage those who think about Q star D to please keep doing that. We could really use some better models, better information about that, and this is going to be tough stuff to do. The betas that we're seeing are higher than we expected, but they're not totally off the chessboard. If you look at some of the larger high velocity models or experiments that are being done at SWIRI, for example, then they're starting to see numbers that extrapolate up towards higher betas for bigger objects as well. So curiouser and curiouser. We do need future investigations into the shear and tensile strength, and see how that works at these higher energies, higher velocities. So we'll see what happens. And with that, I will thank you for your time, and I'll take any questions.
Yeah, I'm very interested in your conclusion there, SPAL matters. Tom Ahrens and I published some papers early on, and we found that SPAL matters. In fact, we kind of depended on SPAL for the delta V's we were calculating. But we started out investigating essentially solid rock, and even for nuclear standoff, where you cook the thing and a big SPAL comes off, it matters a lot. But at about the same time, we came to the conclusion, or I kind of came to the conclusion, that most asteroids are rubble piles, and so they wouldn't SPAL. So how do you stand on that?
I remember that paper very fondly, and I remember we talked about it a bit at the 2013 PDC, and I'm using the word SPAL indelicately, and I thought you might have an issue with that. So what I actually mean is material kicked off of the surface by this sweeping shock wave as it hits the surface, the free surface, and becomes a release wave. So it's not true spall because this model does not include tensile strength, but as the shock sweeps through, it hits the surface, there's a relief, stuff keeps going, and it goes out normal to the surface, and so that has a component in the right direction.
Terrific. I'm glad
So
to see
it's,
you're doing
yeah,
it. We didn't pursue it any further, and I'm happy
Right.
to see that.
Yeah, and I think that so what if, as I remember in the nuclear case, what you were doing there is counting on a thermal expansion, a CTE mismatch, easy for me to say, to kick stuff off. I'm not thinking that we're going to see a ton of that once we go to the nuclear standoff burst, which will be the next round of models. Specifically, this is the impact shock sweeping through, but there may be a tiny bit of tensile strength. One of Keith's papers, the 2003 that I talked about there, talks about just because these are such spiky grains, they might have a little bit of at least internal friction that's going to give them, if not tensile strength, a little resistance in that normal direction. I think we may be seeing a tiny bit of that, but as Megan's models showed in the first talk, it's not a huge effect. So I think there's some things that may rein in beta a little bit, but I don't think it's going to be a ton. Yes, sir.
How far is from the impact point this spall material coming? I mean, it's from the antipodes or halfway to the antipodes, or it's very near to the crater?
So the model has not, I don't have my, I'll show you the figure on my laptop later, but let's see. So no, the shock has gone all the way through in the model I showed you. And as you see, it depends on your shock. So for that case, I wasn't seeing distal spall, although that would of course detract from beta because it's going in the opposite direction. What I was seeing was material that was out to a certain angle that's dependent on your shape and your impactor, that had that positive, or that Y velocity in the correct direction, which I'm calling positive up on the page. But yeah, it's very much dependent on the impact and the target as well. But you will see distal spall, depending on the situation, and we do see that.